Hello folks, this is 2024 October November paper 2-1 and the question number is 3. This question is concerned with the chapter work energy power. So it says and some bit of ERC also present here in this question at the tail end. So the first question says state what is meant by the work done by a force. So when the force applied by a body produces some displacement in its direction, we say work is done. And the formula for work is force into displacement in the direction of the force. Often we have got the cos theta factor here, where theta is the angle between directions of force and the displacement. Now it says a block of mass m is raised vertically at constant speed. The vertical height gained by the block is delta h, as shown in figure 3.1. Derive an expression in terms of m and delta h for the change in gravitational potential energy. For the change in the potential here, delta EP of the block. State the meaning of any other symbols you use. So we have to use other terms as well. So what happens is we have to find the change in the potential energy. So for that we need the potential energy here. So the potential energy here is equal to the amount of work it can do. And the amount of work it can do is equal to force into displacement into cos of 0 degree, because the force is the force of gravitation like this. The displacement is here which is a delta h, let us say delta h, and the angle between them is 0 degrees. So that's it's like f into, it's like this. So f into delta h, and f is equal to mg, so it's equal to mg delta h. So it's the potential energy here. So that's why our change in potential energy delta pe should also be is equal to mg into delta h, like this. So next is an electric motor has input power of this much. So this is a power input. The motor takes a 1.0 minute. It is a time is equal to 60 seconds to lift a load of weight. This is the weight at constant speed through a vertical height of this much. This is the height. Resistive forces are negligible, so that the work done by the motor on the road in this 1 minute is this much. So we have to find the work, and the work is equal to force into the change of height, or we can say force equal to simply this thing. So work equal to this means, so this is force into delta h, and that's equal to the force is equal to, since it is constant speed, the force and this weight should be equal. That's why it's equal to this weight, which is 240 into delta s is 150, equal to, so this becomes equal to 240 into 150 equal to, it is a 36,000 joules, and it is in kilojoules, so it's equal to 36 divided 1000 equal to this much of kilojoules. So this is the amount of work done. Now in the next question we have determine the useful output power of the motor. So our power out is equal to power out is equal to the work it does by time. Work it does is 36,000. We just got it by the time is equal to 1 minute. The time is equal to 1 minute, so it is 60 seconds. So now 6 is a 36, so it's equal to 600 watts. The answer is 600. Use your answer in C2 to determine the efficiency of the motor. So the efficiency is equal to power out by power in, and the output power is equal to 600. This is 600, and the input power is, which was given in the previous question, which is power in 900 watt. So it should be equal to by 900. Sorry, not here, by 900, and that's equal to 2 by 3, that's equal to 0.666666, like this, written as 0.67. So it is 0.67. Now Some of the power wasted in the motor is dissipated by the resistance of its coil. This power dissipated is this much. So this is power loss. Power loss. Now, the coil of the motor is made from wire of total length this much. So this is length. The wire has a cross-sectional area of this much. This is A. This is A. And is made from metal resistivity like this. This is rho. Calculate the current in the coil. So now what it says is the power loss is equal to energy lost by time. And it says that energy lost is dissipated by the resistance, and that's equal to I square R. It is equal to I square I square RT by this T. It's equal to I square RT by this T. And that is T cancel, simply I square R. And since we have given here L, we have been given rho and this A, I square R should be equal to rho L by this A. We need I, so it is I square should be equal to power loss into A divided rho L, and that's equal to, now power loss is 280 into A is this much, which is 2.6 into 10 to the power minus 8, and then rho is this much, 1.7 into 10 to the power minus 8, and L is this much, which is 23, equal to 280 into 2.6 exponent to minus 8 equal to divided 3 into 1.7 exponent minus 8. Yeah, this came to be equal to I square equal to 18.6189 and so on. So I should be equal to root of this thing is equal to 4.314 and so on, 4.31496 and so on, so equal to 4.3 amperes. So the current here is 4.3 amperes.